In this question, we're given three functions, namely the functions labeled here by a, b, and c, and we're asked which of the following could be probability density functions. So what we have to do is just make sure that these functions actually have the properties of what a probability density function must have. So, for example, let's take a look at question A. So the function here is x times x minus 4 as long as x is in between 0 and 3, and otherwise it's just 0. So one thing that we notice right away is that if I look at, say, the function evaluated at 2, well, 2 is definitely between 0 and 3, so I should use the top description of the function here. So that becomes 2 minus 4, and if we actually work that out, that's negative 4. So the problem here is that I actually evaluate this function at a point, and I end up with a negative number, and probability density functions are not allowed to have a negative number. So this is not allowed. Therefore, this is not a probability density function. It's not a PDF because this function was evaluated to be a negative number somewhere in the range, or in the domain. So let's take a look at function B. Function B is x times 3 minus x as long as x is between 0 and 3, and it's 0 otherwise. Now if we took a look here and we test all these kind of points for x between 0 and 3, and we just plug them into the function, we realize that indeed that this function is positive for all the x values you could put in. Actually, sorry, not just positive, but positive or equal to 0. There certainly are no negative values you can get out of the function. So that's okay. So that's good news. But the next thing we want to check is we want to make sure that the integral from negative infinity to infinity of our proposed probability density function is actually equal to 1. So we need to see if this is indeed the case. So let's take a look at that. We do the integral from negative infinity to infinity of our probability density function f of x dx. Now we notice that outside of the range between 0 and 3, our function is actually just 0. So when doing the integration, we don't have to worry about any kind of x values that are not in between 0 and 3. So rather than do the integration from negative infinity to infinity, instead we just do the integration from 0 to 3. And when we're having x values between 0 and 3, we use this version, the top version of our function. So we are integrating a function that looks like this. Okay, and the reason you can say that these two things are equal is because everywhere that is not between 0 and 3 is just 0. So that doesn't contribute to the integral at all, this integral here. So our integral from negative infinity to infinity actually does just end up being only the integral from 0 to 3 of this function here. So let's calculate that. We can simplify the integrand a little bit. This is 0 to 3, 3x minus x squared dx. And if we carry out that anti-differentiation, we get 3 halves x squared minus 1/3 x cubed, and we're going to evaluate that from 0 to 3. So we're going to sub in the 3 into our function, and we get 3 halves times 9, because 3 squared is 9, minus 1/3, 3 to the power of 3 is 27. And then we would subtract off what we get when we plug in 0. So if we plug in 0 into our function, we're just going to get 0 squared minus 0 cubed, so that's just going to be 0, so we don't really have to worry about it. Let's just simplify this a little bit. We get 27 over 2 minus 27 over 3. And if we make this to be a common denominator of over 6, this means it's 81 over 6 minus 54 over 6. Carry out that subtraction, we get 27 over 6, which is equal to, divide both the top and the bottom by 3, and we get 9 halves. Okay, so what this means is that if I integrate my proposed probability density function between negative infinity to infinity, after doing all this calculation, what I end up with is 9 halves. And if it is truly a probability density function, it should be equal to 1. This calculation should have been equal to 1. So this is definitely not equal to 1, so this is not a probability density function. Okay, so let's check these two things for the last function, which is namely 2/9 x times 3 minus x. So certainly, just like we did for part B, we notice that no matter what x value we substitute into the function between 0 and 3, we're going to get a non-negative number, so that's good news. We don't want our probability density function to be negative, so that works out okay. So the next thing that we want to check is whether or not this the integral of this function between negative infinity to infinity is equal to 1. So again, we need to ask, is the integration from negative infinity to infinity of f of x dx, is this equal to 1? And so let's check. So this ends up being the integral from negative infinity to infinity f of x dx. This is what we're trying to calculate for the function that we are talking about. Again, just like in part B, we're only interested in values between 0 and 3 because otherwise the function is just 0, so we don't really care about those. And what we're going to do is, in part C, the function is actually x times 3 minus x, but then multiplied by this 2/9. Okay, so if we actually carry this out, we can take that 2/9 outside, 2/9, and this becomes the integral from 0 to 3 of x, 3 minus x dx. And if we notice, this is precisely, this integration here is precisely the integration we carried out in part B. So rather than do all that work again, what we notice is this integral from 0 to 3 of x times 3 minus x is actually equal to 9/2. So this is equal to 2/9, because we pulled the 2/9 out. And then that whole integral, if we want to repeat all the steps we did in part B, what we find out is that that is equal to 9/2. And if you multiply 2/9 times 9/2, that's 18 over 18. So that's equal to 1, so that's good. So it's non-negative, and if you integrate it from negative infinity to infinity, it's equal to 1. So this is a probability density function for something. Again, we don't know what random experiment it's a probability density function of, but this could be a probability density function of something.